Welcome to qnawire.
All right, so in part A, we need to calculate the acceleration of this box in two different experiments. It has a mass of 8 kilograms. In experiment number 1, it goes 8.22 meters over a time interval of 2.8 seconds. It starts from rest, so it has an initial velocity of 0. So now we do kinematics to it. In order to find the acceleration, assuming constant acceleration. So we know the initial velocity is 0, so that term disappears. 2 delta x squared. Plug in numbers. That's 8.22. Down here is 2.8 seconds. Sorry, 2.8 seconds. Plug in the numbers, and then we get 2.10 meters per square second. And this will be supporting evidence for our answer, so let's put a box around it. Okay, and then in experiment number 2, I guess we're giving the box a slightly smaller push because it only goes 4.20 meters over a time interval of 2 seconds. And again, it began at rest, so v naught is going to be equal to 0. We just use the same equation, so let's just skip ahead to that step. So 2 delta x over delta t squared, plug in numbers, and see that we suspiciously get an identical value of acceleration. That's 2.10 meters per square second. So yes, the boxes decelerate at the same rate because kinetic friction only depends on the normal force and a constant. So kinetic friction. Excellent. Okay, so we are going to need a new slide because this is a data problem and we need a table. So let's go ahead and start setting that up. Boom, 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 boom. Great. And then maybe one more line. That's terrible. Oh my gosh. Okay. There we go. All right, so we have mass in the first column and we're measuring that in kilograms. And then this is total mass, so I'm adding the 8 to each of the values that they give us. 20 over here. And then in column number 2, we're measuring the displacement in meters. So that's 8.22, and 10.75, 9.45, and then 710. Good, and then time interval in the third column, that's where delta t is going to go. So 2.8, 3.2, 3.0, and then 2.6. Interesting. And then initial velocity is going to be recorded here. We haven't calculated that yet. And then lastly, the force is going to go here, lowercase f, and we have not calculated that either. Okay, great. So we have our table all set up. So let's take a look at what kinematics equation we'll be using in order to solve for initial velocity. So that's this one. And then the initial velocity is not equal to 0 because that's what we're using to solve for. So if we divide both sides by delta t, and then isolate delta t. We get this equation. This is what we're using to solve for initial velocity. We just solve for the acceleration. But note that it is a deceleration, so it comes with a minus sign. Plug in those numbers, and you can fill in this column for initial velocities. And then there's a question that I wrote down. The answer is no to. Question is, in each case, did your push give the box the same initial speed? The answer is no, because clearly the four numbers are different. They want us to find the ratio between the largest speed and the smallest speed. So let's take the ratio of V max over V min. So those are 6.7 and 5.5 respectively. Take the ratio of that and you get 1.2. So there's a little bit of spread in velocities. Great. And then in part C, there's another question that I wrote down. The answer is no to. Is the average horizontal force F exerted on the box the same in each case? The answer is going to be no. Sorry, there's also a no in part B. So we're going to use Newton's second law. F is equal to ma in order to solve for this last column. And if you do that into three significant figures, you get 16.8, 23.1, and then 31.5, and then lastly 42.0. So now if we make a plot of what that looks like over here, so we have mass on the x-axis and then force in newtons on the y-axis. So I think it would make sense to go by tens on the force axis and then by fives on the mass axis. So we have 8 and then 16.8 about here. 11 and then 23.1 goes about here. 15 and 31.5 goes around there. And then 20 and 42.0 goes around there. And then you're going to try to draw a straight line that goes to the data. And then this is our equation F equals ma that governs that slope.